Hi, this is Ryan. Welcome to my thesis presentation. We all know that when building a shell structure, the architectural form must be defined before the construction is executed, and this process is called form finding. Form finding is referred to the process of searching for form-active shape with respect to the loadings. In the past, form finding methods are based on experiment, such as Gaudi's hanging chain models. Kangaroo 2 is one of the software that simulate Gaudi's hanging chain models digitally. Today, we'll look at the form finding of Sydney Opera House. When designing this iconic project in the last century, the architect John Woodson imagined the Opera House as a sailing boat approaching Sydney, so he proposed a thin membrane scheme for this project, which is different from today's rib scheme. But unfortunately, he had to abandon this membrane scheme because he could not define the geometry at that time. So this thesis will explore whether a thin membrane version of the Opera House can be designed with the help of Kangaroo 2. Following Woodson's spinnaker concept, two boundary conditions were required in the form finding process. The first one is the anchor point. The shell vertices was set as the anchor points to resemble the connection between the sail and the mast. The second one is the load. The wind load can set the spinnaker. Kangaroo 2 is able to simulate the form under its self-weight as well as the wind load. This image demonstrates the form found Opera House. Shell A1 to A4 are orientated from the right to the left. Then finite element analysis was conducted on every single shell. These four contours shows the stress and moment distribution for shell A2. We can see the maximum value occurs near the support areas. Actually, this result holds true for all the four shells. And these four animations illustrate how displacement propagates under the most critical loading combination. For shell A1 and A2, the maximum displacement occurs at the midspan of the cantilever arms, while for shell A3 and A4, extreme values can be found at the cantilever tips. Then the linear buckling analysis is conducted, and we found the buckling load factors for shell A3 and A4 are below 10. The weakest point under this test is the support areas as well. Therefore, adjustments should be made to increase the buckling capacity at these areas. Now it's time to look at the results from all the four shells. A trend can be seen that the narrower the bottom support, the higher the maximum stress and moment will be. The moment at shell A3 is the highest among the four. Therefore, increasing the support width is a possible optimization approach. And when the support width increases to 4.73 meters, the maximum moment will drop below the ultimate moment strength. In conclusion, form finding software can help produce the thin shell version of the Opera House. However, at the same time, optimization schemes should be proposed to increase the stability of the overall structure. Thank you for listening to my presentation.